Hello, this is Tahsin from Roots of Unity, and today we'll be talking about transformation matrices. Matrices, when multiplied to a set of coordinates, produce a transformative effect on that set of coordinates. For example, matrices that look like this, K00K, transform the set of coordinates by enlarging the shape produced by that set of coordinates. In order to transform a set of coordinates by using a transformation matrix, you must multiply that set of coordinates to the transformation matrix you're using in this particular order. The matrix first and then the set of coordinates. And after you perform the multiplication operation on this, then you'll get the answer as another set of coordinates. And this set of coordinates will define your image. These will be the coordinates for the image produced by this transformation matrix. For example, let's consider the matrix 2002. To transform a set of coordinates by using this transformation matrix, you must write down that transformation matrix multiplied to that set of coordinates. For us, it is 1, 1, 2, 2, and 3, 1. And then we perform multiplication on this. How? We simply do matrix multiplication with this to this. So we multiply this row to this column, 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 and this row to this column. We've already done matrix multiplication before and how to do it. So after you perform the matrix multiplication on this, we'll get the result as 2, 2, 4, 4, and 6, 2, which basically is the coordinates for the image produced by this transformation matrix 2002. The types of transformation matrices we'll be looking at are stretching matrices, enlargement matrices, shearing matrices, reflection matrices, and rotation matrices. So now let's take a look at stretching matrices. What stretching matrices does is that it stretches the shape produced by the set of coordinates and elongates it, like really stretches it out. There are two types of stretching. The first one is stretching along the x-axis, and the matrices that produce a stretch along the x-axis look like this, K0, 0, 1. And what this matrix does is that it stretches the coordinates along the x-axis. A few examples of transformation matrices along the x-axis are 3001. The scale factor here is 3, so see every x coordinate in this coordinate system is being multiplied by 3. 1 here is multiplied by 3, 2 here is multiplied by 6, 1 to 3, and 2 to 6. See? And another example is 5001, and every coordinate in this coordinate system is being multiplied by 5. Every x coordinate in this coordinate system is being multiplied by 5. 1 is being multiplied to 5, and 2 is being multiplied by 5 to produce 10 here as well, and every other coordinate in this coordinate system. And the next type of stretching matrices are stretching matrices that stretch along the y-axis. And what these matrices does is that it stretches the coordinates along the y-axis like this vertically. Transformation matrices which stretch along the y-axis look like this, like 1003, which is stretching this coordinate system 3 times along the y-axis. Every y value is being multiplied by 3. So here it was 1, and now in the image it's 3, here it was 2, and now in the image it's 6. It was 2 here and it's 6 now, and it was 1 here and is now 3. Another example is 1004. Every coordinate in this coordinate system, every y coordinate in this coordinate system is being multiplied by 4. So it was 1 here, now it's 4, it was 2 here, now it's 8, it was 2 here, now it's 8, it was 1 here, now it's 4. The next type of transformation matrices are enlargement matrices, and what these matrices does is that it enlarges the set of coordinates by a certain amount. Enlargement matrices have the following structure, K00K. For example, the enlargement matrix 2002 would enlarge this shape twice. Each coordinate is being multiplied by 2. So here it was 1, 1, and now this is 2, 2. This was 2, 1, and now this is 4, 2. This was 2, 2, and now this is 4, 4. And this was 1, 2, and now this is 2, 4. Similarly, the matrix 4004 would transform this set of coordinates 4 times in this direction. See, each of the sides is increased by 4 times, each of the coordinates has quadrupled or been multiplied by 4. You can also have negative values for k. You can have a matrix like -2, 0, -2, which would also enlarge the matrix, but not in this direction, but in this direction. It would enlarge this matrix 2 times, but in this direction, in the negative y, negative x direction. The next type of transformation matrix we'll be looking at are reflection matrices. And as suggested by the name, reflection matrices reflects a set of coordinates along a mirror line. There are 2 reflection matrices we'll be looking at. The first one is the reflection along the y-axis, which is given by the matrix -1, 0, 0, 1. And what this matrix does is that it reflects the it reflects the coordinates with the y-axis as a mirror, with the y-axis acting as a mirror, and the image is here, so the coordinates is here, so the image will be produced here. And the next type of reflection matrix we'll be looking at is matrices that reflect along the x-axis, and it looks like 1, 0, 0, -1. And what this matrix does is that it uses the x-axis as a mirror, and it reflects the shape and produces an image on the other side of the x-axis. Next comes rotation, and what rotation does is that it rotates these shape forms along the origin like this. Rotation matrices look like this: cos theta, sin theta, minus sin theta, and cos theta, where theta is the degree of rotation anticlockwise along the origin. For example, the matrix cos 90, sin 90, minus sin 90, cos 90 rotates this shape 90 degree anticlockwise with 0, 0 as the center of rotation. And the matrix cos 180, sin 180, minus sin 180, and cos 180 rotates this shape along 0, 0, 180 degrees. And lastly, cos 270, sin 270, minus sin 270, and cos 270, which simplifies to 0, -1, 1, 0, rotates this shape 270 degrees anticlockwise or 90 degrees clockwise along 0, 0. Next stop is sharing matrices. What sharing does is that it translates the set of coordinates relative to how far they are from the invariant line along the direction in which they are being shared. We'll get to all that later, but first let's look at the types of sharing. Primarily, there are 2 types of sharing. Firstly, there is sharing along the x-axis, and the matrices which share along the x-axis look like 1, 0, and k1, and the invariant line for these matrices are the x-axis. Sharing matrices along the x-axis have an effect like this on the set of coordinates. What sharing matrices like this do is that it translates the coordinates of the object in the x direction, in this direction or this direction, depending on the value of k, and depending upon how far it is from the invariant line, which is the x-axis, depending on how far it is from the x-axis, it would be translated in that magnitude. So we'll look at a few examples and it will clear it all up. For example, let's take a look at this sharing matrix 1, 0 to 1. This matrix translates this object 2 times in this direction, depending upon how far away the coordinates in this shape are from the x-axis. For example, here this point is only 1 unit away from the x-coordinate, and it was translated 2 times in this direction. And this coordinate is 2 units away, and it was translated 4 times in this direction. And now let's take a look at this matrix 1, 0, 4, 1. Here this object is being translated 4 times in this direction relative to how far away this is from the x-axis. This point here is only 1 unit away, and hence it was displaced 4 units in this direction. This is 2 units away, and so this coordinate was translated 8 units in this direction. Sharing can also happen along the y-axis, and the matrices that shares along the y-axis look like this: 1, k, 0, 1. And examples of matrices like this are 1, 2, 0, 1, which translates this object 2 times in the y direction relative to how far it is from the y-axis. You know, the y-axis now is the invariant line, right? Another example is 1, 3, 0, 1, which translates this object 3 times relative to how far it is from the y-axis. For example, this point here is only 1 unit away, it is being translated 3 units here. And this point is 2 units away, so it is being translated 6 units up here. However, in some cases, the object itself is on the invariant line. And when this happens, then the coordinates that lie on the invariant line are not displaced in the image. You know, the coordinates just stay there when you multiply it to a sharing matrix. For example, over here, this sharing matrix 1, 0, 3, 1 is being multiplied to this object, and this is a sharing matrix along the x-axis, so this is the invariant line, and these points lie on the invariant line. So the image of this, in the image of this, you can still see that the coordinates are still there. It did not change place. Similarly, when this object is being multiplied to the transformation matrix, which is a sharing matrix along the y-axis, 1, 2, 0, 1, you can see that this is being displaced. These coordinates are being displaced. All the coordinates are being displaced except the coordinates which are here. And you just have to keep this in mind sometimes to solve some problems, that the coordinates that are on the invariant line do not get displaced or do not change. It stays there on the invariant line. That's gonna be all for today. Hope you liked the video, and stay tuned for something special we're gonna be dropping in very soon. Signing off, Tahsin.